If not, then I have to turn off the recording, and then unfortunately we probably won't have record today, video today. But let's try. Okay, now I turn on the video. I'll turn on the recording. Let me switch my window here. Share my screen to see if you can. Okay. I'll write something on it. Can you see it clearly?
Yes, sir.
Okay, so that's good. That's good. It's better than the morning. Okay. Let me still keep the waiting room on, so in case people join later. Okay, so let's do a quick review. It's been a while, right? What did we do last time? We did some examples, right, for the pressure calculation using the hydrostatic principles. And we have those tubes, right? Pressure inside the tube. And we use a manometer to measure the pressure inside the container or a pipe. Okay. Do you remember, right? That's what we did. So we tried to apply the hydrostatic principles. Okay, hydrostatic principle. So what is the hydrostatic principle again? Anybody remember? See, last time we do something like this, right? So it's a pipe, there's a flow in there. Then we have a tube, manometer tube. I think that's the last example we did, right, in last class. Okay, but first of all, what is the hydrostatic principle? Anybody remember?
The principle or pressure? We went over hydrostatic pressure.
Hydrostatic principle. The law of hydrostatics. Okay. This is the principle. That's the only equations you have for the hydrostatics, right? Not only equation, but the major equations. Remember this. After a while, you probably forgot. This is the equation. Okay. What does that mean? I want you to be crystal clear. What's the meaning of this equation? It's kind of like a conservation law. So what's conserved?
Pressure.
No, pressure is not conserved. Pressure is different. Everywhere inside your tank of fluid, pressure is not conserved. If you have a different elevation, you have different pressure. Do you agree?
The piezometric head?
That's right. That's the correct answer. The piezometric head or piezometric pressure. This is the piezometric pressure. These two terms together, P plus gamma Z. It's a piezometric pressure. Piezometric pressure is conserved inside a stationary fluid. Okay, this is your principle, the hydrostatic principle for the statics. Okay, or you say piezometric head is conserved, same thing. P, remember, probably, if you divide it by gamma, which is rho G, both sides of the equation, it will be P over gamma plus Z. This is called piezometric head. Right, is that right? This is called piezometric pressure. Okay. So it's constant. it's constant inside a stationary fluid, okay? In other words, if it's constant, that means at two different locations inside that fluid, the summation of P and the gamma Z are the same. At two different locations, at three different locations, or whatever different, how many different locations, all the different locations, the P always changed due to the different elevation. However, the P plus gamma Z as a whole, it doesn't change. Okay, it doesn't change. So you can always write the equation, say, hey, P1 plus gamma Z1 equals P2 plus gamma Z2. If you correctly marked on the drawing where is 1, where is 2, okay? So that equation is valid. Okay? Or use head form, P1 over gamma plus Z1 equals P2 over gamma plus Z2. Okay, so that's the key, hydrostatic. That's why we can apply this hydrostatic principle to solve the manometer problem like this. Okay, if you are in the flow, you have A and the B point, 2 points. How do you measure the pressure difference between A and B? You can't directly compare A and B, use hydrostatic principle. And the reason is because A and B are in the flowing fluid. In the flowing fluid side, your hydrostatic principle doesn't apply because it's hydrostatics, okay? Between A and B is hydrodynamics, okay? They're moving, is that right? However, you can from B convert to C and D, A and B converted into C and D, because between A and C and between B and D, they are hydrostatics. There's no floating there, okay? Between A and C, it's just stationary. Between B and D, also stationary fluid. The flow is flowing inside the pipe, A and B. But in the manometer, they are all stationary. Okay, if it's stationary, you can say, hey, piezometric pressure at A equals to piezometric pressure at C. You can directly convert the problem into B, C, and D for the measurement of A and B. Okay, so that's the process. Okay, we did it. You remember last time for this problem, we did 2 different methods. Remember, one is the one equation method between A and B, going down plus, going up minus, going up minus gamma Z plus gamma Z, right? That's a trick, a shortcut, okay? A different ways to solve the problem. But you can always use piezometric pressure, hydrostatic principles, A and C, so you can convert A and B into C and D. C and D, between C and D, the pressure difference is obviously from the manometer fluid. The deflection of the water level between C and D indicates the pressure difference between C and D. Okay, so we talked about it in last time. So look at the notes. I should have that problem in there. Okay, this is the review. Okay, this is the principle. Piezometric pressure is constant in a stationary fluid. So next project, video project, which will be due 2 weeks from today, is to verify the hydrostatic principle. Okay, you do an experiment to measure the hydrostatic principle we learned here. Okay, the requirement, everything is similar, is the same as last time. The grading is the same. Okay, the time length of the video is also the same. Hopefully after today, you're familiar with how to submit, how to upload to YouTube or other platform, and how to submit. Then next time will be a little bit easier. Okay. Okay, any questions on this, on the second video project? Good. Okay, so today we are going to introduce the plane force, force on a plane surface. So far in chapter 3, we're all talking about the pressure, point pressure, basically a pressure on a location, on a point, okay? Now, we're gonna go one step further, okay? So how to calculate the force on a inclined surface, okay? Let me use the next page. Since it's a shortened semester, I'm gonna cut some of the material. So the derivation of those equations, I'm gonna cut it short, okay? Let me just give you the solution, the expression, equation for the solution, right? How to calculate the force. What is the equation for the force on a inclined surface? But I like us to draw that. Okay, so you have an inclined surface down here. Okay. If you have the coordinate system, this is the O, let's say this is the Y direction. This is the surface, this is under a fluid water, let's say. Okay, let's have a plane, a front view. Let's say the arbitrary geometry. This is the X direction. If your eye is here, if you look at it, it will be a surface like this. Let's say symmetric surface along the X direction. And the plane direction, let's specify as Y direction. Okay. So what is the force on this plane surface? So we have to introduce some of the, okay. First of all, the force will be equals to okay. I put a P bar here. Okay, P bar indicates the average pressure on the surface. Okay, average pressure on the surface. So, oh, that makes sense, right? Average pressure times area. A is area, okay, of the surface. So it will be the overall hydrostatic force on it. Okay, so how do we calculate the P bar? Okay. Every surface has a center of area. Okay, if you had statics, we talk about this in the static class, right? This is called centroid. Or center of area. Okay, the pressure on the centroid of the center of the area, we can use this as an average pressure. Or pressure on the centroid. Okay. So that's easy, right? If you can identify the central location. So how do you calculate the let's say the depth, water depth on the centroid is H. So what is the pressure on the centroid? Anybody? So you have a central location. Let's say the water depth is H on the central location.
Is it gamma Z?
Yeah, gamma Z, right? Gamma is rho times G, right? Specific specific weight, okay? So gamma H, right? You say, did I say gamma H or gamma Z? In this problem is gamma H. H is the water depth on the centroid location, okay? So there's some trigonometries there, right? You have to identify in a practical problem, probably you need to identify the H. You maybe give you an angle theta here, or let's say like I have angle alpha. Okay, this is the plate. Let's say I give you the distance between the centroid and the surface is called y bar. It's y bar here. Okay. Okay. In the textbook, we introduced the y bar in here. Y bar is it's not the water depth on the central location. Okay. It is distance between the surface to the centroid along the plate direction. Okay, you understand the y direction, right? From surface along the plate direction. Okay, y bar. So you probably, in order to solve some problem in the future, you probably need to identify one of them, either H or y bar. Okay, and if you want from H or from y bar, you can calculate H. If you get H, you directly solve the problem. Okay, identify centroid. So where is the centroid of the geometry then? I think that's probably your next question, right? So I think you needed the textbook. There is in this section, a lot of people feel difficult because the geometry. In a practical problem, you need to solve some geometry problem. So turn to page 639. Okay, let me take a picture. If you don't have textbook, but it won't be too clear, I suggest you to get a copy of this page. Okay, let me send it to you in GroupMe. Then you can take a look if you don't have textbook. Okay. Did you see it? So if you look at that page, this is appendix, I think it's appendix figure 8.1. Okay. It gives you the 4 or 6 shapes. The plane surface could be any shape, right? So if the problem give you a shape like this, one of the 6, okay, the cross is identified is for the center. For some shapes, the center is obvious, all right? Circle, the center is just center, okay? Oval, the center is also the center, okay? For the rectangle, sure, it's in there in the middle, okay? But for triangle and for the half circle, the cross, the location of the cross indicate the center location, okay? And it gives you a dimension. Look at this. Where is the cross on those shapes? Okay. It gives you the dimension, then it gives you the exactly location of the center. In a practical problem, in the problem you're going to solve, you will see a different shape. For example, I'll give you a triangle, okay, under the water like this. You need to find the pressure on the centroid, right? So you need to have exactly dimension and find out what is y bar and what is H in order for you to calculate the pressure on the centroid. Does that make sense? Okay. This is some geometry. Okay. If you're not familiar with this, spend some time after class to look at those geometry. Okay. I think it clearly in this figure appendix figure A1, it clearly show the center. So if there's an inclined semicircle under the water, okay, you need to find where exactly the center is in order to find exactly the water depth on top of the center. Okay, if you can find that, you find the pressure, the average pressure. Okay, your average pressure is basically the pressure on the center. Is that clear? Clear to everybody? Then if you have an average pressure, you should be able to find the pressure, find the force. Okay, find the overall force on that plane surface. Okay. Any questions? This part is the most difficult. This part will be the most difficult part if you solve problem. If you in quiz or whatever, you will see, okay? A lot of problem could be very difficult to solve, okay? Let me know if you have questions, okay? Now, another thing I want to introduce here is, this is called, now this is the center of area, right? Centroid. Another thing I want to introduce is called center of pressure. Okay, center of pressure. Why we need a center of pressure, first of all? Well, look at this. If this is a force plane, okay, what is the pressure distribution? Should this be the pressure distribution? Everybody agree? Huh? Why is in the bottom of the plate has a higher pressure?
Because there's lower elevation.
It's low elevation, okay? It's a linearly change, okay? Because it's gamma Z, right? Gamma H, so it's first order of H. So H changes, the pressure linearly change, okay? Linearly increase. Oh, because of this, maybe I need to know a center of pressure, right? Center of pressure means that exists a point that the pressure is balanced about that point. Is that right? Center of pressure. This is the pressure distribution, right? So is the center of pressure in the middle of the plate?
Not always.
Not always. This is called centroid, right? We already did in the previous example. Centroid. What do you mean by not always? In which kind of situation they are? I think you're right, not always. If the plate
area is uneven.
No, we're not talking about the area uneven. We're talking about the plane surface. So it's a plane surface. Per area is kind of evenly distributed. Okay, I think you're still right. Not always is always a good statement. You don't say too absolute, right? Not always. The situation that the central is center of pressure is when the plate is horizontally lay underwater. If it's horizontally lay underwater, where is your center of pressure? Okay, let's say my plate is here like this. What is the pressure distribution on top of it? Okay, is that right?
It's even.
They're even. So if it's even, your center of pressure, sure, it is equal to the centroid, center of area. Okay, Good. So your statement is right. In case that indeed there's a situation that the center of pressure is equal, the same as the centroid, center of area. Okay. But in the case I draw in the right, are they equal? Are they the same points?
They are not.
They are not. Which one's lower?
The higher up you go, the lower the pressure.
No, I mean, these 2 points, centroid and the center of pressure, which one is lower? I'm talking about center of pressure, right? That's a location, right? There exists a center of pressure. I just don't know where it is, right? Now I'm kind of know it's the center of pressure is not on the same point as the centroid. Okay, so where is the center of pressure? Is it above it or below it?
Be below it, right?
Why is below it?
Because of the angle that you drew it.
Because the angle I drew. Okay,
It
this
doesn't
is
really matter because there's less pressure on top and there's greater pressure on the bottom.
that's right. That's so on that point, on the center of pressure, all the pressure would be symmetric, would be evenly it'd be balanced. Okay, so the overall force on the left of the point should be equal to the overall force in the right of the point. All right, is that called center of pressure? Is that right? It should be balanced. All the force distribution should be balanced about this point. So because the bottom is a higher pressure, so you have a lower area down there. Okay. So in the top, you have a lower pressure, so you have a larger area. So then the top, bottom and top balanced about this center of pressure location. Okay, that's why center of pressure always below the centroid for a inclined plate. Well, of course, we're talking about the in the x dimension is like a symmetric. You don't have to change. If you change the x dimension geometry, then it will be different, right? We'll only look at the 1D y direction, right? So I assume the area is about the same along the x direction. So then, sure, your center of pressure is lower than the centroid. Okay, it's always lower. Okay, so I can, let me draw a new page. Then we need to just find out where is exactly this center of pressure is. And it's very important point for you to solve problem. Let's say this is still y dimension. This is called y bar, right? This is centroid, center of area. Let's say we give this, let's say YCP. Okay? Everybody understand my drawing here? Okay. So it's not starting from the starting of the plate. No, it's not starting from there. It's starting from the water surface. Oh, water surface. Okay, that's by definition. Okay, y bar is not from the center to the top of the plate. No, it's not. Y bar means, by definition, it means from the center of the plate to the surface, water surface. Okay, then YCP by definition is the center of pressure, from the center of pressure to the water surface. Okay, so how much bigger? What is YCP? Why we need a YCP first of all? So you're learning this in order to solve static problem, right? Okay, static problem, you need a free body diagram. Okay, so the overall force on this plate is a distributed force. A distributed force like this doesn't help you solve problem for force balance. Okay, right now, we managed to calculate the entire force. This distributed force, we are able to calculate. It's equals to force which is the full pressure on the centroid times the overall area. That's the overall force. As I draw this distributed force on this plate, that's the overall force value we should be able to calculate. Okay, so if we draw the free body diagram, this force F, where do I draw that arrow to? So now in the real problem, I'm gonna get rid of these arrows. No, we're not gonna draw those arrows for solving a free body, a static problem using free body diagram, right? Now I know the overall force on the plate, okay? I need to draw one arrow to representing this combined force. Okay, do I draw the arrow on the centroid? Or do I draw the arrow, the big arrow on the center of pressure at this force?
Center of pressure.
Yes, center of pressure. Okay, okay. That's why we need to identify where the center of pressure is. Okay, for a static problem, hey, the overall force on the plate is easy to calculate by this. Okay, we can calculate it out, no problem. But the problem has other components, right? We need to have a force balance. Okay, this is just one force, combined force. And then I use a big arrow to represent this combined overall force on the plate. Okay, I have to point this arrow into a point. Okay, that's the center of pressure. That's by definition, this combined force should be applied to the center of the pressure, where the location where the forces are balanced. Okay, this is the purpose. This is the purpose why we want to introduce this something called YCP. We need to know how to calculate the YCP. Okay, so YCP, I skipped all those derivation. Okay, in the previous semester, I always spend a class on the derivation, but now let's skip it. I just give you the expression that you can calculate. Okay, this is the expression. Or people move y bar to the left-hand side, become YCP minus y bar equals to I bar. Okay, we actually introduced something new here, right? Y bar is okay. Okay, be careful. In the calculation, it's not from the, it's not the half the length of the plate. It's not, okay? It's from the centroid to the surface. Okay, surface of the water. Oh, okay, this is the definition of y bar. So you need to plug in, substitute the correct number for the correct calculation, okay? Y bar is okay. Area, well, you should be able to find out. On the appendix, I sent it to you in GroupMe. It also showed the area, the expression for the area for all 6 surfaces, all 6 shapes, okay? So you should be able to find, but just be careful. Be extremely careful in calculating those things. And what is I bar? I bar is the second moment of the, actually it's called the moment of the inertia of the area, okay? Moment of inertia of the area. I skip some of the derivation in here, but it should be in your statics chapter 5. Textbook, okay? It should cover that second moment of area. Basically, it's moment of the inertia of a plane surface. Also, in that same appendix, it gives you the expression for I bar for all these 6 shapes, okay? I don't think I will give you any problem for the shapes outside these 6 common shapes, okay? These are all the shapes you need to worry about for any quizzes, okay? But for all these shapes, if you look at the GroupMe, the file I send you, okay, for these shapes, it also gave you a expression for I. It said I bar XX, it doesn't matter, it's just the I bar in this equation. So it gave you expression, for example, for the rectangle, the I bar equals to B times H cubed divided by 12. What is B and what is H? Be careful. B is the bottom length, right? The bottom width. H is the height of the rectangle, okay? Be careful. Again, this is the geometry, a lot of geometry in this part of the fluid mechanics here. Okay, so for the triangle a little bit more complicated. I bar will be what? BHQ divided by 36. What is the B? B is the bottom side. H is the height of the triangle. It's not the side, it's a height. Okay, so follow this definition for i's, for the moment of inertia of the surface. Okay, so with the calculation of I bar based on these expressions, you should be able to calculate the exact location of YCP. Okay, that's the exact location of YCP. After you know this, then you can point your arrow on that location. So you may ask why I need to know the location and point an arrow to it. Don't forget, for the rotating problem, you need the moment, the calculation of moment instead of just the force balance. Okay, moment, how do you calculate the moment? For example, I put a hinge on top of this plate here, it's a hinge. This plate gonna rotate about this pivot point, about this hinge. Okay, what is the moment? The rotating moment. How do you calculate the rotating moment? That will be this force times the arm length between where the force is to the hinge, right? Your rotating moment will be F times this length. But again, this length is not YCP, but it's related to YCP. Okay, YCP minus this distance between the hinge to the surface, to the water surface. That's actually this distance for the arm distance, right? Okay, or you can say it's a half of this length, half of this length. No, the half of the plane length, maybe I said D, based on the centroid, plus this distance. What is this distance? Is this distance, let's say, D2? Is this distance D2 the YCP minus Y bar? Okay, that's why I need this equation. If you know YCP minus Y bar, then this is D2. Then you plus the half length of the plate. That will be your arm length. Okay, so that's the moment. In the moment calculation, really, we need to know exactly where this F pointed to in order to calculate the moment. Okay, that's why we here need a YCP. Okay, any questions? Is that good? So you have two equations now. This is the equation, and this is another equations. Okay, now you have the tool to solve some more complicated hydrostatic problems. Let's look at the example. Example is actually a difficult problem. So that's a textbook example. 3.10 in your textbook. Any questions? Please jump in. Okay. Okay. Example 310. Okay. So it's kind of like a reservoir. Then you have a pipe going into it. Well, it's a circular pipe with diameter 4 meters. Okay, but when you cut at an angle of a cylinder, if you cut an angle, it's not vertically cut the angle. So now you cut the pipe. This is the water. They cut the pipe like this, then install a gate on it. This is the gate. This is the hinge. Okay. What is the shape of this end and the gate?
Rectangle.
Rectangle? No, it's not rectangle. It's a circular. It's a circular tube. If you cut the circular cylinder with an angle, what's the ending area?
An oval.
It's oval, right? Oval shape. So it's an ellipse, right? So with this shorter diameter 4 meter, and with the longer diameter 5 meter in this problem, here is 5 meter. Okay, is that right? So let me ask you, why they want to cut the pipe like this and add the door there? Why not just vertically cut and add the door there?
Is there a like, what is the hinge holding on like a plate to block the water from going in or something?
Yeah, it's a hinge. Then it's a gate. It's a door. It's a gate cover on the top of the surface.
If they do it vertical, the hinge wouldn't be as effective because the pressure of the water is holding the hinge. And
Exactly. If you cut a vertical door like this, you know, you have a flow force coming in, right? So it's underwater, hydrostatic. Well, what about the force on the other side? Nothing. What happened to this door? It will open inside, inward, right? Unless you force it to close. Is that right? This is the gate, right? But if you cut with the angle, with the ellipse shape of gate, what happens? If the force pushing it, water force pushing it, what happens?
Gate's too big to swing in.
Yeah, it cannot swing in. It's an automatic design to close the gate. Okay. That makes sense? Yeah. Okay. So that's a purpose. It's of course outside of the scope of this question, of this problem, but that's the purpose people design something like this. It can automatically keep it always closed. Okay, as long as there's water on top of it, it always close. It won't leak water out. Okay, but if you want to open it, it's another story. You can push it open from the other direction, right? Okay, so that's the problem statement. So that serves a purpose. Okay, that serves a purpose. Okay, so what the question is? Let's see. Okay, dimension. Okay, this pipe is 8 meter deep from the top of the pipe to the water surface, 8 meter. Okay, and what is the force required to open? What is the force required to open this gate and then let the water come in? What's the normal force required to open it? Right now, if you want to open this gate, you can only open outward. You cannot open inward. Okay, you open outward. So you're gonna apply a force to the other side, right? Why you apply force to this side to open it? Well, that's obvious, right? That's why where you put the door handle on the other side of the door comparing to the hinge. Is that right? You open the door handle is always in the other side because it's easier. Because the moment is the force times the arm length. In this case, this is the longest arm length. It's 5 meters. That's why you want to open it. You open it from the bottom because the hinge is in the top. Okay, so that's the situation. So this is a very practical problem. Okay, so that's the design for the pipe and for the door open like this. And then what's the force required to open it? So if you want to open it, how much force you want to apply to to the end of the gate. Okay. Ooh, you see difficult problems, right? How do you solve it? If I put this on your quiz today, so it will be difficult, right? So how do we solve? What's the strategy? Problem solving.
Do we do a free body diagram first?
Obviously, right? Of course. Before you can write down the equation, you without the free body diagram, you basically your mind is blank. What do I write it down? What equation I should write it down, right? Maybe after you draw the free body diagram, it will be more clear to you. Okay, you can write down something to earn some points. Okay, when I grade it, I just look at, do you have those steps? Okay, so this is the gate, ellipse-shaped gate. I need a force to open it. Let's say F. What else? Any other forces? Free body diagram. Let's say that I put a letter here. O, point O is the hinge. Right? Any other forces on this?
You have the pressure.
I'm asking for force, right? Free body diagram. You don't say pressure. I know what you mean, right?
The force due to pressure.
Force due to the hydrostatic pressure. Okay, hydrostatic force maybe. How about that? The force from the water. Okay, so okay, where do you draw that big arrow?
At the centroid or center of pressure.
Slightly below the centroid.
That's right, slightly below the center. Both of you are right. You have to draw that force. The force is applied to the plate, slightly below it. Okay, that point to the surface of the water will be YCP. Okay, now maybe you want to draw some letter use some letter to representing this distance. Let's say D. How about that? I kind of out of letter. How about D? Because I'm eager to write down an equation. The value I don't have, you know, that will stop me from writing equations. I put a letter so I can use that letter for the equation. Okay, I put down the equation, Dr. Zhang will give me points. Okay, I'm eager to do that. That's why I put the letter here. Okay, this is hydrostatic force, let's say FH. Okay, anything else? That's it. We only have two forces, right, on this problem. It said in the problem, you ask, hey, maybe that the gravity, right? But it said in the last sentence, it neglect the weight of the gate. So the gravity weight is neglected. Okay, so then no weight on this problem. Okay, so that's it. That's all the force available for this problem. So immediately after you draw this, you can write down the equation. So which equation you want to write? Summation of force equal to 0? Or summation of moment equal to 0?
Summation of force equal to 0?
No, they're not actually. Summation of force equal to 0 is difficult to write. Not good for this choice. If you want to really see the force, then you need to have a Rx, Ry on the hinge. Because you detach, remember the rule of thumb of drawing free body diagram. If you detach the object from another object, which in this case you detach it from the hinge, you didn't draw the pipe, right? You detach it, so you have to replace by the reaction forces. In this case, is Ix and Ry. If you talk about summation force equal to 0, you have to include both Ix and Ry. Did that make sense? Okay, to me, that's very, very important for you to understand this for solving a static problems. If you see a rotation problem, this is a rotating problem. The door is rotating. When you open and close, is rotating. If a rotating problem, don't do summation force equal to 0. Okay, instead, you do summation of moment equal to 0. Because when you do summation of force equal to 0, the reaction force you have to include how difficult there will be if you're including the reaction force Rx, Ry. Instead, you probably want to go with summation of moment about O point equals 0. Okay, because you know the Rx and Ry do not contribute anything on the moment about O. Why is that? Because from O, yeah, go ahead.
It's because the radius is 0 at that point.
Yeah, because the arm length is 0. Okay, to the O. See, Rx and Ry is exactly on the O, so there's no moment. Okay, so you don't have to consider the Rx, Ry in your calculation, which is much simpler. Much easier for you to do. Okay, that's the rule of thumb. When you see a rotating problem, after you draw free body diagram, you choose the moment equal to 0 equation. Okay. If you pick the moment balance, so how do you expand it? How many moments in this problem?
2.
2. Okay. One is from the force F, the other is from the force FH. Okay. So counterclockwise is positive, right? Is that right? In moment, we define counterclockwise positive moment and the clockwise is negative moment. So be careful with the sign. So in this case, which force gives the counterclockwise moment?
The FH.
FH, that's right. FH first is positive. FH, what is arm length? You do not need to find exactly what the arm length. I use the letter. See, I draw the letter D on the drawing, right? I write the letter D on the drawing. That's for the purpose. Write down the D first. Don't worry about the details later, okay? F times FH times D. This is the positive moment. Which one is the negative moment? Minus F. What is arm length for F?
5 meters.
Just 5 meters equals 0. Okay. If this problem is 10 point, if you can reach to here, probably you get a 4 out of the 10. Okay. If you can reach to this line, okay. I may give you 2 points on the drawing, 1 point on the summation moment equal to 0, 1 point on this. Maybe you get 5 out of 10 already. Okay. Does that make sense? I want to show you how I grade it and to show you how important, which steps are the important steps. Okay. You write down this, you can leave the rest of it to your intern. Hey, intern, come. This is your practice. Go ahead and do it. If you are the engineer. Okay. You give the direction, right? So your boss give you direction, you do the work, basically. Very important, okay? The moment balance for this problem, and then expand it to this form, this equation, okay? So in this equation, is my unknown in this equation? What's the problem example ask us to solve? When you reach here, you just look at, hey, if my unknown, if my goal is in the equation, my unknown is F, the force required to open it, good, it's in the equation, that means it's right, I'm happy. Okay, I'm happy, F is there. So in order to calculate the F using this equation, what do I need to know? What do I need to find out?
FH and D.
FH and D. You know, that gives you the hint for the next step. Okay, that's why I follow this engineering steps to solving problems. Always guarantee a solution. So next step, you can just write down. My goal is to find out the FH and find out the D. After I get these two calculated, I solve the problem for F. Okay, is that right? Is that the thought process, problem solving process? So which one is more easy to find? FH, F, and a D? Well, similar difficulty, right? maybe my FH is easy to find. How do you find the hydrostatic force? You still remember? Anybody? You can, if you don't remember, you can just write down the equation you remember. Let's equation remind you. What's the next step? Is that the equation? Okay, is that right? Can I find the area? I think area is for ellipse is in the index, right? What is the area? I think it's there, right? I don't remember. Sometimes I just need to look into it. You don't have to remember everything, right? Appendix, okay. Area of the ellipse, it's there. Oh, pi AB. Okay, what is A? What is B in this problem?
Is it 2 and 2.5?
That's correct. 2 and 2.5. Be careful. It's not 4 and 5. Okay. Area A and B are both radius. Okay. So it's 5 pi. That's my area of the ellipse. Okay. So the area is given 5 pi. Okay. Everybody agree? See, write down the equation. Let the equation tell you what to do. Okay. That's my philosophy for solving problems. Okay. So what is P bar then? What is the P bar? Conceptual wise, what is the P bar?
That's the average pressure.
Okay, average pressure. What do we use to represent the average pressure?
Rho H.
No,
Not rho, sorry, gamma H.
no, we use the pressure on the centroid to represent the average pressure. Can you remember this sentence? Everybody?
Could you say that again?
We use pressure on the centroid to represent the average pressure of a surface. Is that understandable?
I thought that was gamma H.
That's right. I'm just talking about the concept. I want you to explain it. What is H? What are you talking about H? So how do you find H then?
The height from the water level to the centroid.
That's right, centroid. You're using a point pressure to representing the average pressure. Okay. That's what we have in the, do we have it in the previous slides? Hold on. Okay, look at this. Oh, further. Okay, here. I want you to fully understand this. Okay, did you see that my H here? Okay. Force on the plane equal to the average pressure times area. The average pressure is the pressure on the centroid. Every point has a pressure. Do you agree? Every different point on its inclined surface has different pressure. But the centroid has its pressure. So what is the gamma H here? Rho GH, H, what H? I draw on the drawing. Did you see this? H? Did you see my point here? Is that right? That is the pressure on that center of area location. Okay? Find a pressure on a certain location is the pressure, is the gamma times the depth on that location, so-called rho GH. Okay, is that right, everybody? Okay, so the pressure on the central. So where is the central of this ellipse? What is the water depth on the ellipse?
Do you have to use Pythagorean's theorem? And then add that to 8?
Okay. First of all, let's put a letter H here. Okay. Gamma water is given times H times 5 pi. Write it down. Gamma is 9800 water. Okay, not a problem. 5 pi is given. So now find out the H for me. It's not really difficult to find out this H. But you have really need to know the H is water depth on the centroid location, on the center of area. So that's why for solving any problem of the surface force, you need to know exactly where is your centroid. Where the centroid is, you need to know exactly where it is in order for you to find the water depth on the centroid. Is that clear to everybody? Any questions? I don't want to continue before everybody 100% clear on this. Is there any question? Anything not clear here? Is that good? Conceptual-wise, okay. So basically, what you're calculating the force is basically is just to find out where the centroid is, find the centroid pressure, okay. Pressure on the centroid, on the center of area. Then times the area is overall force, okay. So now a little geometry here. What is H? Give me a value. Is H 8 meter?
It'd be slightly more than 8, right?
Yeah, obviously it's more than 8, right? It's a little bit deeper than the 8. Okay, how much deeper?
8 is equal to 10.
It is equal to 10. The reason is here, if you draw a line here, is it connected to the center of the circle? Okay.
It should be.
Yeah, it is, right? Center, of course, that's the same cylinder. No matter how you cut it, the center will be at the same center, same height as the center of the circle. Okay, so what is the diameter of the circle?
Diameter is 4.
4,
Okay, so what is the radius then?
2.
2. 2 plus 8. Is that 10 meter underwater?
Makes sense to me.
Yes, that's good. So gamma times 50 pi. Oh, come on. Okay, it's 10 meter. Okay, h is 10. So basically you calculated the FH. Halfway through, remember you need to find out both, right? FH and the D. We calculated FH easily. Okay, so next time we'll continue to find out the D. D is more tedious. Okay. Okay, is that good? Hey, everybody. So far, so good, right? I'm just want to slow down, but make sure everybody understand. Use the class time to fully understand the content. Okay. Good.
Dr. Zhang, what was
Yes.
that you were saying earlier about having a force meter to verify our equations for the project?
Okay. F equals to ma. How you verify this equation? You cannot say, hey, my F is equals to mass times acceleration I measured. No, that's not the verification, right? You verify it both sides of the equation. F equals to ma. You have the equal sign, right? Your
Yes, sir.
left and the right. Left and the right, you have to, both of them, you have to measure it using the independent methods. For example, how do you measure the F for the apple dropping from the tree? Newton, right? Newton find the apple dropping from the tree. You have to weight it. Weight the apple. You know that's the force.
Okay.
How do you get ma? You measure the mass, measure the acceleration. Let's see if they are equal. That's called verification of an equation. So both sides of the equation, you have to use independent methods to measure, then to see if they are equal. That makes sense?
Yes, sir.
Okay. So that's the key of doing experiment. Okay, very important. Yeah. Good
So,
question. Yeah.
For mine though, I had the sigma L equals mass times gravity because it was static, and I used that to solve for my mass. So I need to go back and resolve for another one to verify it.
I don't know how you solve for mass. You probably want to measure the weight, right, directly.
I don't have a scale like small enough to measure the weight.
Yeah, just find some way to, maybe you put the 100 these small items together to weight it, then divide it by 100. That's the weight of the individual.
All right.
Right?
Yes, sir. Thank you.
You're welcome. Any other questions for anything? I'm here to answer. Okay, I guess that's it for today. Okay, so in 2 weeks, it will be your second video project, okay? Have a good day. See you Wednesday.